great to meet each other in person, but like it's still the pandemic, and we all hope that like, you know, at some point there will be real conferences again. But for the time being, I think we all got now used to like being over Zoomed and being in meetings like that. And so let's try to make like a great workshop out of that online event here. And I hope like, you know, to spark some ideas with like, you know, the talk that I prepared for today with the title that George already mentioned, Machine Learning Meets Visualization. I'm really honored for the invitation. Thanks a lot. So, and like as the title already says, I want to talk a little bit about like, you know, the relation between those two areas and like report on the experiences and the work that we have done, but also discuss some of the challenges. I hope you can see my screen and everything is correct. If not, I assume that George would be shouting at me already, which is not the case. So I think we can go ahead. So let's start now. Okay, so I thought about, let's start with like a little bit of a historic view, because I also felt like, well, you know, it's 2021, and like I felt like, oh, I'm getting older. And then I like reflected and thought about the time when I started my research career. And the big motivation, I think, like for my work, but probably also for many of you guys' work, was data. So I started like around 2006, 2007, when I entered like my PhD program, really being motivated and doing some research with data. You know, 15 years ago, I feel like, you know, people really figured out how to store data, how to put them into databases, stuff that like you guys also probably like know much more about than I do. But like I thought, okay, this is really, really great. And my background was more in HCI, so in human computer interaction. So the main idea I had, the main passion was really trying to bring data to people. And so it turned out there was a lot of need to do that. And the combination of HCI plus data for me quickly resulted in doing a lot of visualization research. So we worked together with automotive engineers, for instance, but also with musicians that had some data, or with people that studied architectural data. And we were building all these crazy nice, or like at least from our perspective, nice visualization tools that could help them to solve and to get insight into their problems and data. So at the end of this decade, so around 2009, 2010, I think it has become clear that data is really fundamentally changing society, science, and industry. So there was the fourth paradigm of science that you for sure know about, which was a very influential book and statement. And that was the time when I started my postdoc at UBC in Vancouver, Canada. And I met people like, you know, Kevin Murphy, Kevin Leighton Brown, Nando de Freitas, who all did research in machine learning. And that was a really fantastic area, I thought, and it was actually diving into that area. So that was a time when NIPS, or now NeurIPS, happened in Vancouver, and it was still, I would call it like a normal size conference back then. So it was like, you know, the same size roughly as IEEE VIS or other conferences, but not like the huge thing that it is now. And for me, it was clear that there's like, you know, this really interesting relationship between machine learning and visualization, but I think also for other people, where machine learning was more bringing this like, you know, algorithmic view into data analysis, and visualization was bringing much more this human-centered angle, this person user-centered view into the game of how people can interact and work with data. And then I think you know all what happened over the last decade. Machine learning exploded. Like conferences like ICML, NeurIPS, they got huge. People are investing lots of money. Like, you know, there's huge courses. There's like industries. Data scientist has become the top of the year, and all those sort of things. So like this is what I try to, and I realized later on it's looking like a coronavirus graph that's like, you know, some funny or not so funny coincidence here, but like, so in this coronavirus graphic, we see like machine learning, this algorithmic view has really taken over. And around that, there's these gray circles, which illustrate that I think there's like a lot of other research areas that all of a sudden became interested in data analysis. And when they talked about data analysis, they mostly meant, at least in my experience, machine learning, and not so much visualization or visual analytics, which we have been working on. And this is nothing negative. I think this is like, also for the visualization community positive. But all of a sudden the Viz community was more for me like, one among other communities. And I thought like in some ways, like I'm still sticking to my future picture of like, in the end, I feel like, data should be mostly helpful for people. And so I feel like, things are becoming more interesting here if we create tools that help people to work with their data. There's another keynote later today on democratizing data, right? It's all this like, bringing data to people. And for that, we need not only the great algorithms that we get from machine learning, but we need also the interfaces, the ways of how people can work with, think with, and solve problems with data. So, and this is sort of where like roughly 10 years ago, I really started in thinking about this relation between machine learning and visualization and how these fields can benefit from each other and how we can combine them. And I think this is what I thought can be a good topic for today's keynote here, and these two questions. And I want to structure that into 3 parts. So the first part is really how can we leverage visualization research for machine learning, so for machine learning engineering and also research, but also vice versa in part 2, then how can we leverage machine learning for visualization, design, and research. And then this third part, I want to do a little bit more forward looking and like talk about the combination of like, visualization and machine learning together, and specifically talk about the challenges that I think are ahead of us and are worthwhile doing research on. Okay, so let's jump into the first part already, visualization for machine learning. So as you all are very likely aware of, there has been like a huge hype, a huge discussion around all topics that are summarized under the umbrella of explainable AI, explainable artificial intelligence, explainable machine learning. And I think in the visualization community, there has been a long discussion that visual representations are, of course, at the heart of communicating models, AI to people and to explain those things. And there have been like, great papers out there. So here's, for instance, like one of the early papers, which interestingly did not come from the machine learning community, but not from the Viz community, but from the machine learning community on explainable neural networks. And you probably all know what these visualizations say. They illustrate like, the different levels of a deep neural network, and like, they help you for an image classification to see how a computer sees these images and uses that information to classify images. Many other things, like simple things like explaining gradient descent algorithms, optimization, can easily be done with visualizations. There's like online tools, online tutorials that like use visualizations in a very nice way to illustrate those sort of algorithms that are used in this like, wider framework of machine learning models. But also like things like TensorFlow, you probably by now find for each type of machine learning approach, each machine learning model, you find some sort of like visualization approaches that can help in that realm. And this has also been something that we've been working on, but as compared to, I think a lot of the other approaches, which are model and approach specific, we always have been working on something that we thought is more general. And it's like a model agnostic framework, which we call visual parameter space analysis. Yes, it's a long word, but the ideas I think are rather simple and straightforward, but I hope, and I also think they can be helpful for many problems if you just adapt this way of thinking on how we can use visualization to better understand all sorts of different models. So the core problem is really that we want to understand and select a quote unquote good machine learning model among many others. So it's like this idea of ensemble modeling. So we're creating many models and then want to understand, use visualization to understand the space of models. And today I want to use like a specific type of input-output model or input-output algorithm to illustrate that idea of visual parameter space analysis, which is like dimensionality reduction. Why because we have been done like dimensionality reduction for a long time ourselves. So we're eating our own dog food here, and we can use like, the parameter space analysis for selecting good dimensionality reduction algorithms, hopefully for a problem at hand. So let's just briefly recall. I'm pretty sure that most of you are familiar with dimensionality reduction, but like, if not, what is dimensionality reduction? Why are we caring about that in visualization? So you start with some data, say on cars. So you noticed I'm from the University of Stuttgart. So like, we're building cars here in that area. So it's a always good example to use that. So, and then we have like, some high dimensional data. So we have many different dimensions. We use some dimensionality reduction algorithms like the venerable PCA, MDS, TSNE, UMAP, ISOMAP, you name it. And then we project the data down into like a lower dimensional space for visualization, most commonly into a 2-dimensional space, but it can also be 1 or 3-dimensional. And then we use visualization, typically like a scatter plot to show our projection. And I'm pretty sure many of you have done some dimensionality reduction in your lives before. So the question now that we have been focusing on is like how to select a good, quote unquote, dimensionality reduction algorithm for your problem, for your data at hand. Okay, so we did 10 years ago, a field study where we tried to find out how actually do people select these dimensionality reduction algorithms. And so we found that most of them would just like engage in what we call trial and error process. So you start, it's illustrated here, with the first algorithm. Many people start with PCA because this is what we learned in primary school or a little bit later. And then like you check your data and you might be happy, or more likely you're unhappy. And then you engage in like trying out other algorithms. So you might try out TSNE, which is a parametric dimensionality reduction method. You set the parameters, you're even more unhappy, you try a different parameter setting, and you're not seeing the patterns that you want to see in your data. So we thought that this is maybe not the most systematic and most straightforward process, because like there's many issues in sort of like you forget what you have been looking at, you're not systematically exploring the space. So instead, we said like, let's use this idea of visual parameter space analysis, which is essentially we're sampling that space of models. So we're sampling the space of algorithms here. So we see here algorithm 1 with parameter setting A, algorithm 1 with parameter setting B, algorithm 2 with parameter setting A, and so on and so forth, and create a space of outputs. In our case, these outputs would be simply projections, so scatter plots of the same data set. And then we create some visual analytics interface that allows the analyst to now see how these different parameterizations, how these different algorithms are performing and compare them. So we did that for like many different input-output models, but here like we're focusing on dimensionality reduction. And so we have these plots, and essential component of many of our tools that we build for VPSA, visual parameter space analysis, is what we call like a meta map or a similarity map, where we use dimensionality reduction or projection techniques again. So we do like, sort of a meta plot. So like we have many of like these projections, we organize them in the space. And the important thing is now that like, the distance between those two, each of these 2 points can be interpreted as the similarity between those two. And so let me briefly illustrate that with one of these tools that we built for that purposes, which is the VisCoder tool that we built together with my PhD student, René Couture. And so here you see like a typical thing, and it's meant to illustrate a little bit of the typical tools that we're building in our group. And also I think in the visualization community, more generally, you often find those. So we have a multiple coordinated view system. And now here in the center, we do have this meta map, as I said. So like each of these points, I'm not sure if you can see my mouse. I hope you can see it. So each of these points are essentially is a projection. And like if 2 of them are close to each other, then it means to a human observer, they look similar. So and then like we have also here, this is the output space. Here we have the input space. We're just focusing on T's and E for now. So we have a two-dimensional color palette here, like we have the perplexity and we here have the epsilon. But like you could also, of course, look at other dimensionality reduction methods that we included into that sampling process here. So let's look at a video here. So we have like a lot of features, like, you know, the background encoding that you're seeing here is essentially encoding, like, you know, the differences between this low dimensional embedding and the high dimensional embedding that we're seeing. But the more important thing is the linking and brushing, which can be really helpful here. So we see, like, if I'm brushing here, now I'm brushing in the output space. Let's stop that for a moment. I'm brushing here in the output space, similar projections. So all projections that I selected look similar to a human observer. And now we can look over to the input parameter space, and you see that all of these seem to have, like, you know, rather similar perplexity values. The epsilon, however, is all over the place. And now we can just continue. We moved it over. So, like, you know, in this local neighborhood, it seems like, you know, all these plots, they have similar perplexity values, but the epsilon for all of them is all over the place. We also can turn it around. For instance, like here, we select all the plots that have the same perplexity, and we see those are all in close proximity in local neighborhoods. If we do the same for epsilon now, we select, just wait a sec. Now we have the epsilons. You see they're jumping around all over the place. Okay, so what did we learn? This is usually the time for some audience speaker interaction, which unfortunately is not working so great in the online presentation modes. I would just tell you, we learned actually about some very interesting sensitivity phenomena here, right? We learned about, like, you know, how much do we need to tweak an input parameter in order to get some output parameter changes. And so what we saw is, like, perplexity has a very nice, neat behavior. So, like, you know, if we crank the perplexity parameter, then, like, we also see some, like, changes in the way the projections are made and look to a human observer. If we do the same for epsilon, like, it's all over the place, either, like, you know, it's super, super sensitive or it's not sensitive at all. So there's an interesting insight that we could make through this visual parameter space analysis interface here. Okay, so as I said, I think, like, this visual parameter space analysis, as we see it, is really a general model agnostic framework to analyze all sorts of input-output models, not just dimensionality reduction algorithms, but all sorts of algorithm models that you have on your desk might fit into that problem definition here. And historically, in fact, I think it has not been used for machine learning, but I think the origin of visual parameter space analysis comes much more from classical simulation models and algorithms. So, for instance, some of the early works that we're seeing here is from where we used it, for instance, for an image segmentation algorithm. So, like, you know, see a brain segmentation. We also used it for bird flocking behavior. So how do swarms of birds form over time? Other people have used it for, like, you know, things like, you know, showing some visual effects, flood simulations, like, you know, designing some needles for surgery, and all sorts of different simulation problems. So the thing that we tried that visual parameter space analysis framework for over the last decade was really all sorts of machine learning problems. We found it fits actually really well. So I just showed you that example of dimensionality reduction. But the first thing, the first set of algorithms we initially started with was actually clustering algorithms. So the idea is the same. You just sample all sorts of different clustering algorithms with different parameters. So k-means with different k's, dbScan with different parameters. And then you can get, like, a global overview to analyze and compare these different models, these different algorithms to each other. Similarly, with classification models, we had a paper at AVI last year. So it's not in submission anymore, it's already accepted. And we also, like, use similar ideas for active learning models, for instance. Okay, so this concludes the first part of the talk where we talked about visualization for machine learning. Now we're switching gears, we turn around. But now we want to look at, can actually visualization researchers benefit from the great progress that has been made in machine learning? So here's our coronavirus looking overview graph again. What was sort of surprising to me, at least up until 2 or 3 years ago, is that the Viz community mostly focused on visualization for machine learning. This is very nice of the Viz community. So like, trying to help machine learning researchers to better understand what's going on. But if I looked around, all the other communities were maybe a little bit more selfish, and we're talking about how can they use machine learning as a method to do better research in their own areas. And this is what I call machine learning for visualization. And as I said, 2 or 3 years ago, it was really surprising because there was very little work on that, I think. But now things started to change, and many people also work on that area. So let me illustrate what I mean with that. I think there's many problems, visualization research and visualization design problems that can benefit from the use of machine learning. And here I want to focus on one of the grand challenges in visualization, which is designing good visualizations. And you've probably seen visualization designers, visualization researchers giving talks before. We all have these fantastic illustrating examples that show how good and how important it is to do good visualization research. So here's one of them. So we have some data with just a few points, and we have 7 dimensions, and then we plug it into like a visualization tool. Most people would just do Excel and then use some visualization, and then you say have like a 3D bar chart, which we probably already know this is not the best idea. And then we want to see the pattern. Who's seeing the pattern? Okay. Oh, I heard somebody. Okay.
Yes. This is George. I tried to find the part.
Okay. Okay, George, let me ask you, can you see the pattern now?
Yes.
Yes, of course. So everyone sees that. This is the typical sort of examples that we are getting in visualization. So I changed now the visual encoding from a 3D bar chart, which is like a not so good visual encoding, to a heat map where we used color to encode the values that we're seeing in the table. And now it's obvious that there is this question mark, right? Everyone sees that pattern that's sticking out. And sort of there's many examples, but it's this is an artificial example, but this is exactly the core challenge in visualization. And if we're dealing with more complex data, it's about how we aggregate the data, how we visually encode the data to actually reveal the interesting patterns, the interesting structures in the data. And so people have been working on that problem for a very long time. And the classical approach to find out which of the visual encoding techniques work better for certain patterns was running user experiments. So you essentially, you build 2 different versions showing the same data in different ways, like, here, Jean-Daniel and Goniam with adjacency matrix and node link diagrams. And then you run a user experience, you invite people to the lab, you measure task performance and errors, and then you derive some guidelines. So this is all great. However, the issue with that approach is that essentially you just get rule of thumb. So you can't really automatize that information. You can't really make it useful in algorithms. And of course, you have a very high cost of running these studies over and over again. And so approximately 10 years ago, people started with this influential paper. I think Mike Sips was one of the first ones who really discussed that. So the idea is really to have measures. And I think in the database, the KDD community, you guys are very much aware of measures are all over the place and they're used. The difference here would be that in the visualization community, people would like to have measures that measure how valuable a human observer finds some data set. Okay, and so here, we can focus on a specific problem instance to illustrate it. So let's assume we have some multi-dimensional, high-dimensional data, and we want to find the visualizations, the scatter plots that are interesting to a human observer. And now, of course, we first need to define what interesting means. And one thing that many people focused on, and also our work focused on a lot, is class separability. So the assumption is you have a multi-class data set, and then you want to see projections that are actually separating your classes. So the blue, the red, and the black class in that example, rather than those that just mingle everything together. And so they proposed some like interesting algorithms how you can do that. Very straightforward. For instance, this a centroid-based measure. So we're essentially just like compute the centroids for each of these classes, and then you iterate over all the points. So like if a point, the blue point here, is closest to its own centroid, the measure like goes up. This is something good. However, if another centroid is closer, like in this example, the red dot is closer to the blue centroid, the measure gets punished and the value of the measure goes down. And then you just iterate over all points and you get a score. And then you can actually use the score to find the good views in like a high dimensional data set. So like, this is only 5-dimensional, so that's not that interesting, but like you can imagine if you have like, some 200 dimensions, then you quickly have something like 20,000 views, then those techniques become really handy. Okay, so I got really fascinated by these approaches, and we actually used them for our own problems, but we realized that there is an issue. And the issue is that the techniques that were proposed did not generalize well across different data sets. So they worked well for the toy data sets and the data sets that were tested in the papers, but not for others. So how we found that out was by running a qualitative data study. So essentially what we did, we looked at like 816 different scatter plots and used different measures on those. And for instance, for the centroid measure, we found and that by just like observing and qualitatively coding the behavior, that in almost half of the cases there was some sort of issue with that measure. And for only the real data sets, almost like 70% of the scatter plots resulted in some issue with that metric. So this is the time when I started talking with my colleague Michael Opetit, who comes from machine learning, and he said, well, essentially what you're having here is like a machine learning problem, or like even more specific, it's a computer vision problem. So for those of you who come from the field of computer vision, please forgive me to have like a very naive understanding of computer vision. But for me, it's essentially what computer vision is doing. We have images of cats and dogs, and then we want to build an algorithm and feed this algorithm with an image that the algorithm has not been seen before in the training phase, but the algorithm still can tell us like this is a cat. Isn't this abstractly the same as what we try to do in the visualization community then? So for instance, here we can feed training data in terms of like, scatter plots with separable classes and scatter plots with non-separable classes to a machine learning model, and then train it. So like later on, when fed with some unseen data set, it can help us to say like a human would say this is a separable or a non-separable class. And so this was the core idea that we started working on in 2013. And then we published like the first paper on it in 2015, where we really just had like, very easy, straightforward implementation of exactly that process. So we gathered a large collection of like around truth data. So this is like human beings giving label and really just binary, like a class is separable or it's not separable to a large collection of data. And then we predict that with different quote unquote models. Those models are essentially just our measures. So you can also think about them as features. And then we evaluate the quality of each of these measures. And like we just like the quality evaluation basically works by saying like, how well is the model predicting the human judgments? And from the machine learning literature, we know there's many ways of how we can do that. So we picked a very simple one. So we picked the area under the curved bootstrap here. I'm not explaining in detail, you probably, most of you know anyways what I'm talking about. If not, don't worry. Essentially what you can interpret that x-axis here is essentially if you have like, 50%, that means it's just a random guess of the algorithm. If you have 100%, then this algorithm, this measure would do a perfect prediction of the human data that we collected before. And so the results looked actually quite promising. And in fact, the centroid measure, the ones I introduced before, worked best from like the 32 measures that we identified here. So with an average of 82.5 AUC, which means there's, of course, still a 20% improvement. And also, I think some other thing, we selected only very clear-cut examples. So that explains the differences to what we've seen before. So this was very handy, and it illustrated sort of like, that we can automatize that step of like, instead of running user studies over and over again, we're actually collecting some data, and we can train different models and compare them. So equipped with that information, we now were able to say, like, we can now create as many measures as we want and evaluate them based on our model of human perception. So this is what we did. So we created approximately 2,000 new measures by just systematically exploring the space of how we can model a scatter plot visualization. So this is lots of fun. Like, you can use like different neighborhood graphs, proximity graphs. We tried out the Delaunay graphs, KNN-G graphs, many others, and what we call purity functions. So like, how do we split that graph based on the labels from the data that we see? And so this is something that we can use to model this human class separability. And we found that actually almost 60% of our new measures already outperformed the best state of the art, the Centroid measure. So those were quite good results. And the best measure reached out to like almost 93% average AUC. So this was a pretty cool and like very quantifiable result that we got from that line of research. Now you might, of course, ask, okay, Michael, this is very theoretical and I'm actually bored. So like, why should I care about like, points in scatter plots? I know this is a scatter, like in visualization research, we really love scatter plots. Ron Rensig once said to me something that I really like: scatter plots are the fruit flies of visualization research. They're like complex enough so we can learn something interesting about them, but they're simple enough so we can still like, generalize and like connect it to like generalizable laws. So this is why you probably see visualization researchers often that talking about scatter plots as their fruit flies. But still, we want to do something like, in the real world. So we already saw that, we can help humans finding interesting views in a scatterplot matrix. So we already said, like, for 5D, that's probably not that interesting. For 10D, it's not either, right? We can do that manually. But if you go up to 200 dimensions, then you have like approximately 20,000 views. Then it's already helpful. And of course, you think, hey, Michael, didn't you tell us before about dimensionality reduction algorithms? Like, why should I like, do all these axis aligned projections if I can do like, a non-axis aligned linear projection or even a non-linear projection? And this is something that we also then did. Using these perceptual measures that we just created, we fed them into a linear projection method. So like something like an LDA, linear discriminant analysis, but with a different optimization criteria. So we fed in the human perception as a way to drive the dimensionality reduction process here. And we actually got very good results. And in our studies, we found that like, for people, our results were even better than the venerable LDA, for instance. But you can also do other tasks, okay? It's still scatter plots, but now like a lot of people ask like, hey, where does this assumption come from that you always have class labels? No, we don't always have class labels. Sometimes you just have unclassified data, and then you have monochrome scatter plots essentially. Then we're talking not about like a class separability task, but we're talking about something like a clumpiness or like, class identification task. And there have been methods for that, like, the skagnostic measure of clumpiness. You can also use, of course, like classical clustering algorithms like dbScan for that. So we created, on using this method that I just proposed, was gathering like, some data on the human perception. We created a method that is called ClustMe. And then we actually showed in a series of experiments that at least for a human observer, this method can bring some very beneficial results. Other tasks, I think like, at some point we went crazy and like, using this idea of like, seeing visualization as this optimization process, specifically with my collaborator in China, Yunhai Wang. We use that idea like of optimization to a lot of different visualization design problems. For instance, here, the problem that we said, like, how can we assign good colors to scatter plots? And good colors is, in that case, means that we can separate the classes well. And so we created this like optimization function again. And here you can see those are the ones that are like, not so good. Here's a red class, here's a pink class. For a human, it's really hard to discern them. But like, here, this is some ranking, some like, color assignment ranking that was scored high by our method. And you can see like the classes are more separate. And of course, we also can use that to other visual encoding. So finally, I'm going away from my beloved scatter plots. And like here, we're seeing some stream graphs. And like, the issue we're having in stream graphs very often is like the sign illusion. So here, for instance, like, if you go down, you would think, oh, this is thin, although like, it's actually the same as it would be over here. So we use an optimization function. So this is from previous work. And like we used a novel optimization-based function here to optimize these plots, and we showed that like we got better results. Okay, cool. So there's hopefully I convinced you by now like that like this way of thinking about like using the machine learning pipeline can help us to optimize the visualization design process. So maybe like a high level or like really a bold claim would be maybe this ML based visualization design gives us really a new paradigm of doing visualization design and research overall, because things are changing. So now there's scalable data, and I think this is like also now getting to the core of what this workshop is about. Scalable data becomes available. So, and there's many papers now, but like just the VisNet, I think, was one of the first ones that got really to a pretty large number or big number of data sets that they collected. 31 million data sets crawled from the web that can be used to fed into such processes and such models. At the same time, also the methods, I argue, get more scalable. And of course, like it's the machine learning and the deep learning hype that like, really pushes that. There's like essentially new developments coming out of that community every month or even every week. And that's really great. So hype is really not meant in a negative way here. There's a lot of things that we can try out. But at the same time, also in terms of like gathering the human perceptual ground truth data, there has been a lot of work on now using online studies, mechanical Turk studies to gather that sort of data. And I think specifically now in the pandemic, right, this is something important. There comes new challenges with that, but most of our studies in that realm are online now. And like this is very different as compared to 10 years ago. Okay. So if I lost you, now it's the time to come back. We're switching gears again and come to the final part 3. So we talked about Vis for ML and ML for Vis, and now we want to bring them together, okay? So this was the holy grail sort of that we thought about. So isn't there something like a human-centered data interaction, like a visual machine learning that we can use to really bring those areas together? So why would we like to do that? So here I want to quote Michael Jordan. So in fact, the image on the left here you see is Jeff Hare. Some of you probably have heard of him. He did many really good Viz papers and a lot of good Viz research, and like also has companies or one company that does that. And he gave a talk in Stuttgart. I think it was the last talk that we had before the pandemic hit the world. And like he had this quote of Michael Jordan from UC Berkeley. So it's not the basketball player, it's the famous statistician. But he has a really interesting quote that I very much like, which is, we need well thought out interactions of humans and computers to solve our most pressing problems. And I think I'm just bringing that here because that's a statistician. It's not a human computer interaction person or a Viz person that tells you. But I totally are bought into this argument that, we need to leverage the things the computer is good for and the thing that the humans are good for together to solve like the really pressing problems that we're seeing. So in some ways, I think a lot of this stuff that I have not talked about today so far, the application-driven projects that we're doing. So I told you, like, in the automotive industry, working with engineers here on the left, but also here on the right, like working with text data, working with journalists that want to organize their space. They often fall back into some way of combining some algorithmic component, some machine learning component, active learning, whatever, with some visualization interface. And I think like, the close marriage of those two is really, at least in our experience, often a good way to really pragmatically and beneficially tackle the problems, the data problems that users have out there in the wild. So before, like, talking even more about, like, some of our previous work, I would like to dive now into really the challenges that I see at the intersection of machine learning and visualization research. So challenge number one, I think, is really, and I'm not saying that people have not done a good job, but I think like we need to continue is really solving real problems. So in fact, so I think a lot of my early work focused on exactly that. So we created this like design study methodology, which essentially is a way to do interdisciplinary studies between visualization, data-centered researchers, and domain experts. It's sort of like a user-centered method for data and like visualization heavy projects, which differ from classical HCI in that like the problems are more complex, and you can't use, for instance, method like a pure observation, because like you can't just look into the people's head. And so there's a lot of implications, but people really did that. There's different types of these like problem driven and like application driven studies. So one angle of the attack is really the domain problems itself, but there's also other angles of attack that I think are very interesting. For instance, like, Michael Oppermann and Tamara Munzner published a paper last year on data first design studies, where you actually start with like the data and you try to visualize it, and then you reach out. So in fact, with Michael Oppermann, he did his master's thesis in my group, and like we worked with data from city bikes, so from bike sharing networks, and then we reached out to all sorts of potential interest groups that could work and be interested in that data. It's a really interesting project, but we have not started by like the problem, but we started by like ideation and creation here. Along those lines, I think like what we were not seeing that often yet is like a model first design studies, where we really start with certain types of models. I think they're becoming more and more, and then like we reach out to people and still try to bridge this gap. And essentially, to go full circle here, I think the most important thing is still to not forget like these problem first design studies, which is the original idea in some ways. But so what are all these problems about? And so very often I'm actually nowadays referring to my work not as a visualization researcher, but I would more call it human data interaction or human model interaction. Because essentially visualization can be one way of how we as humans interact with our data, but there's many others that are equally important. And I feel like, if we look out into the world, more and more everyday tasks might get involved into like, data-rich processes. Like you want to catch the bus. You can think about like, okay, now I get a point estimate. Okay, and the point estimate is often wrong. And no, like in the pandemic, it's really like an example that we're longing for, like, catching the bus. That would be lovely. But you can imagine like, showing some sort of uncertainty visualization that encodes like, the delay that buses have. And it would be actually interesting also to compare that, of course, among different countries. And I assume that Germany wouldn't be that good as they always say, but that's a different story. Okay, so people have done that, and I think like, one paper that I really like is the paper by Sedlmair, Amershi, and colleagues from Microsoft Research, 2012 at Kai, where they actually combined active learning with the task of like, I want to, like another thing we would like to do in the pandemic, like, run a party with my friends and like invite them from Facebook. And you just, sample sort of like, a few friends that you would like to invite. And then the algorithm, the active learning model in the background recommends you additional people that you probably also should invite if you select sort of people. So it's really about the collaboration between the man and like the human and the machine. So we also did something along similar lines where it was about listening to music, something that we published at IUI. And the idea is really, all like these recommender systems, Apple Music, Amazon Music, you name it. And like here, we were unhappy with the situation that like it was always a black box recommendation. And so we used keywords as a way to bring human feedback into that loop and to like, allow what we call the left turn. So I allow for serendipity and exploration. And in fact, so we tried it out, and at least I identified many cool new metal bands that I'm now listening to. So I think this was a really interesting project. Did they involve visualization? probably if we sent those papers to the visualization community, they would have said, no, 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 like it's not complex visualization. But I would still argue it's like an interesting data problem. And I see it like that way, that the Viz community at the moment, I know, like, we're not the Viz community here, but like most of the stuff I see there, it's still like, this old school Photoshop, like, many features tools. However, the world in some ways has moved on to like, little toys, little hammers. They're exactly good for one single nail, for one single problem, like an app, for instance. And I think there's many of those data problems that we have not been working on, and there should be more attention to those, at least in my humble opinion. Okay, challenge number 2, along similar lines, interaction. Another thing that I have been wondering about very often is this notion of interaction. And like what you see in many of the visualization applications is something that we call linking and brushing. So this is what I showed to you before, like, I brush something here and I can link it to like, the same data instances in another view. This is, I think, a really powerful interaction approach. But the question, of course, is this all? Is there not more? Like, it's in the end, like, we said, like, this is human data interaction that we want to work on. And there's a few, I think, really interesting things that I would like to see more research in those directions. So one is this entire stream of work on semantic interaction by Alex Endert and other folks, Remco Chang, those people have been very active, where we actually like do direct interaction, for instance, in a scatter plot by bringing 2 points closer together. And by doing that, for instance, we can change, in this example, dimensionality reduction on the projection, because we hypothesize actually those should be together, and then I can update the model in the end. So I'm learning from human interaction, and there's like, now coming more and more work in these areas, like there's MLUI workshop, for instance, that deals exactly with those sorts of questions. Interactive learning, it's going the same route. So like, I'm providing labels, and we have done a lot of like, work on like, how can we leverage human labels in the process of like, making them human and the machine work together better. But also post-WIMP, and I feel like, the UbiComp and the HCI community, they have done a splendid job in like, doing all these sort of things. If I look at the visualization community, we're still doing like mostly like mouse and keyboard, right? It's great for certain problems, but like I think there's so much work out there. There's so many interesting design spaces, specifically now with like things like immersive analytics, situated visualization. We in fact have done a lot of work over the last 2 to 3 years in that realm as well. Something I have not been talking about today, though. Okay, the core question when we talk about interaction, of course, is like, when is a human in the loop needed, and how should we bring this person in? So this is a diagram that I've also been using over the years that helps me to think when a human in the loop is actually needed. Because often, like, if you come from a machine learning angle, the colleagues from those areas, they would just, hey, we could have just used machine learning to solve your visualization problem. So I think it's important to characterize what makes the problem a visualization problem versus like a machine learning or automatizable problem. And so this graph here, I think, can be helpful. So we said, like, it's really about the information location. So like the information location can be, for instance, in the head of the analyst, or it can be like externalized into the computer. So the assumption of like having automatic solutions means that all the information needs to be externalized into the computer. And so this explains, for instance, like, there's not just a simple like button that we need to press and then like our algorithm completely solves like cancer, right? All on its own. But we still need to get like the tacit knowledge out of the heads, the externalized knowledge into these models. And I think visualization is a good tool to do that. At the same time, on the y-axis, we see task clarity. So in a lot of the projects that we've been working on, task clarity was an issue. The task is not like, I want to throw a coin into a vending machine, or like, even something that I would argue is like rather well-defined is like driving a car. But like a problem like solving cancer is inherently very ill-defined. It's fuzzy, and like we can't like, easily break it down into subtasks. And those are the problems that we've been working on in that space. And very often, the typical visualization contribution is to move a problem toward more automatization. So like we help people externalize some knowledge, and like we make also the task clearer. And that's great. In the end, it might look a little bit depressive, so because like in the end we're all like, you know, unemployed because all the problems can be automatized. Fortunately, that's not the case. So Jason Dykes and his colleagues wrote a great paper, like, you know, discussing that notion that like whenever you move forward, at the same time you essentially get 10 new questions that you can look at in that like space of ill-defined problems. And I would even argue, I think like at the heart is really still like the science of interaction. That's also an older paper by Bill Pike and colleagues arguing that like, you know, we really need to study these ideas of human data interaction. Okay, and last but not least is I also think we need to more heavily think about scaling up visualization techniques and algorithms and approaches. And I think this is why I think you guys are doing a splendid job. This is exactly the right direction. If I now look at typical machine learning data sizes, I feel like, you know, they're big, right? If I look at typical visualization data sizes, compared to that, they're pretty small. At the same time, the time requirements for machine learning, they're much smaller than the requirements for a visualization problem. In a visualization problem, we usually want to build some interactive interface. So at least in a few seconds, we would like to get some feedback, if not in a few milliseconds, to allow for interactive rates. And of course, that can explain that, but I think it also shows the need that we need to have like, you know, better, more scalable methods. So what can we do along those lines? So first of all, kudos to you guys, and also like people from LDAF. I think there are some sub-communities that think that, but there's still so much work to do. Something that we've been working on with, for instance, Jean-Daniel Fekete at INRIA is progressive analytics. And I think like this is really something I personally feel we need to dive much more into. So you probably know progressive algorithms like progressive JPEGs, or the traditional ways you just like, you know, old web sort of thing. You build up like this cat image over time. And then like, you know, it costs you really a whole lot of time until you see, oh, it's actually a cat. The progressive approach on the right is like, you know, you add more details over time. We could use the same metaphor for visualization. So you start with a rough overview, like, you know, okay, sampling, subsampling some points, aggregating some points first. And then like, you know, use that in all sorts of visualizations that have this challenge of like, you know, providing interactive frameworks or analytical frameworks, at least, while still working with reasonably sized data sets. So there is some work. So we had a Dagstuhl seminar, or time flies, at 2018. We're still working on the book. Hopefully it's coming out soon. And also people like Nicola Pazzotti, I very much liked his steerable progressive TSNE implementation. So I think people really work into that area, and I think it's an important one towards more scalable methods. Okay, I think like, you know, we're hitting the end now. So let me briefly conclude. We talked about three things. So first, visualization for machine learning. We mostly talked about this idea of visual parameter space analysis and used DR, dimensionality reduction, as a way to illustrate that. Then in the second part, we talked about machine learning for visualization and a potential way to automate our design decisions in visualization. And then finally, we talked about the challenges, or at least some of the challenges. There's, of course, way more at the intersection or the combination of visualization and machine learning approaches. So what about the future? I'm actually optimistic, but I think this is like, you know, in the general nature of a scientist. So there's things now popping up. There's like, you know, the data centers. There's, centers for human-centered data science in the States. There's like a whole lot of work on explainable AI, trust in AI. I think there's like more and more topics are popping up that are all at this intersection of machine learning and human factors, user interfaces, visualization. So I like to use that figure here to conclude my talks, because for me, it's really like the combination of machine learning and visualization is really a core ingredient for the human lens to data. And if we think back into the past, there were things like the telescope and the microscope, and they fundamentally changed how we understand the world. And today's world is mostly going to a different medium, which is data. And we need visualizations, we need interaction to work and understand this data. And I think like, this will bear out like a lot of new findings on how we understand and work in our world. On that note, I want to, of course, thank a lot my team and all my collaborators. Without those, of course, like the work that I presented today would not have been possible. And then last but not least, of course, thanks a lot to you. I hope you enjoyed the talk at least a little bit. And now I'm happy to take any questions. Thank you very much.
Thank you, Michael. Thank you very much for this presentation. It was very, very interesting, and I think it certainly covers a lot of the questions we have also in this workshop, and I hope that all of the participants will find also very interesting this presentation. So we have, let's say, about 5 to 10 minutes for questions. I don't know if any one of you want to ask something, Michael.
No need to be shy. I'm not biting, and even if I were to, it's not possible because we're online.
I don't see. You can raise hand or just take, unmute yourself, whatever you feel. Okay, so I have a question. I will mainly stick, to your last part, to the last part of your presentation regarding the future challenges and how we can, let's say, work on that. My question has to do with whether do you consider that the human in the loop will actually provide new insights that, let's say, algorithms and traditional algorithms cannot give for getting insights out of the data. This part is not very clear to me, or at least it's not very clear how, let's say, the human can provide new insights regarding existing algorithms or new algorithms and machine learning models that, let's say, can provide output from the data. Maybe this is a part that combined with the interactive analysis, as you mentioned before, can give new challenges in our community as well. So the question has to do what human in the loop can provide on top of existing ML.
Okay, so this is a very good question. Thank you very much. I think it's also a very broad question. So let me try to answer with some thoughts that are in my head. For me, really from an application-driven point of view, let me start with an example that I think illustrates that well. So we've been working with automotive engineers a while ago. That was with BMW when I still was in Munich. And so one of their challenges was essentially to detect errors that they were not able to characterize before. And so this is why, I put this figure here. So in some ways, they were clear on the high level, they want to detect an error, but they couldn't really specify what that error was about. So for instance, it was this one error where just all of a sudden all the 4 windows were going down in the car. Nobody would know where this error came from. And then they used all their tools and they couldn't find it. And so when we stepped into this process, we created a tool that allowed people to externalize their domain knowledge. And then they have people sitting in Munich, people sitting in Dingolfing, they all externalize their domain knowledge. Back then it was through state machines, pretty old school. But and then they plugged them into an analytical framework and used the expert knowledge from different experts to make sense of the data. And then they finally detected the error. And then they moved along this path, because as soon as they detected the error, they could automatize detecting all instances of that error in the future, right? And I think this is still happening nowadays with all of these problems. And this is why sometimes doing visualization research, I think in my opinion, and specifically applied one, is really hard. Because telling these stories is hard. In the end, it's just, well, just write an algorithm. It's an easy algorithm to detect these problems. But it's the process to get people to get the tacit knowledge, the things that they have learned, combine also the knowledge from different people, and then make that into an algorithm. And the second part of my answer is, okay, the making it into algorithms in some ways has become easier and harder at the same time. Like things like, you know, in active learning, interactive learning, they're exactly made for that sort of purpose, but they're mostly studied at the moment for, like, you know, really simple, well-defined task. Okay, this is a cat, this is a dog. But how about like labeling things with, like, you know, hundreds of labels or ill-defined labels? So we've been working with people, like, you know, where like the labeling task is not that clear. And like, you know, and then also dealing with, like, you know, the biases, like, you know, that you bring into these models from people. But I think very often it's about the type of the problem. It's the ill-defined problems where we need to do that. And this is also not new. So like Herb Simon in the 70s actually has characterized it. And I think like he got the Nobel Prize for his work, right? If I remember correctly. So that's really something like, it's this, like, you know, almost wicked sort of problems that we need to work on. And then, like, you know, I think what really has changed is this need to externalize and use that, reuse that knowledge in models. This was a generic answer, but it could go on probably for much longer, but I'll stop here.
No, thanks. I think it covers some of my, at least, you know, questions. So I think we have time for just one more question. I don't know if anyone of you would like to ask something, Michael.
George, I have a question. Hi, Michael.
Yes,
thank you very much for the talk. My question is related to the incremental visualization you told us about. What do you think are the main challenges in incremental visualization from the data management perspective? For example, works related to incremental user-driven indexing.
Okay, I'm not sure if I 100% understood your question. So the incremental visualization, you mean the using machine learning to? You mean that part, or?
I think a few slides. Progressive use.
Oh, the progressive.
Yes,
okay.
progressive.
Yeah. Okay. Oh, yeah. Okay. Yeah. In the
Yeah.
end, I talked about the progressive stuff. Okay, the progressive incremental.
So I'm asking, what do you think are the data management challenges in this setting?
Yes. Okay, that's a very good question. Sorry, I like for one moment, because I sort of just mentioned that as a side note. Yes, that's also Nikos. That's a very great question. So we're working together with people from the database community, and we had this dark stool with this idea to bridging like the Viz community and the database community. Myself, I'm not a database person, but I think, like, you know, one of the challenges, and there were 2 seminars in dark stool that walked along like similar lines. The first one was to develop an understanding, a mutual understanding of like the problems in the first place. Because, like, you know, I think like I remember, like, you know, a few days of discussions where, like, you know, Viz researchers would say, hey, you know, these are like our challenges, and database people would say, oh, this is easy, like we solved that 20 years ago. And I think, like, you know, now there evolved this, like, you know, more common understanding of like people like, you know, we need to do, like, you know, quick databases, like, you know, more iterative. Also, like, you know, it has an impact on the queries that you post to databases in terms of, like, you know, you need to quantify uncertainties, like the sampling technology. So some of the examples that we've been talking about for these progressive solutions are, for instance, like, you know, if you just like go down your table, like you might like your progressive summary, your iterative approach might not work, because all of a sudden you have, like, you know, some systematic changes in your data. So you want to assure things like random sampling, and that's apparently, if I understood the database people that we had on board there correctly, those were some of the challenges that they were seeing. And so, like, there's also now people working on those sort of problems more. So Dominic Moritz is, for instance, one that is also reaching out in the database community much more heavily. So I have to say, like, you know, I always like, I work with like, data management people, and they do a splendid job. And like, it's sort of like, I go then on top visualization perception more onto these higher levels. Yeah. So I'm not sure how helpful this reply was, but at least we have like, one or two chapters also in the book exactly about databases.
Okay, thank you very much, Michael.
Okay, thank you, Michael, for this keynote. I think now we have a very, very small break. Let's say 10 minutes, and we will proceed with the first session with the research paper. Let me just ask you if you can reconnect. I will end this because there is a...
George, I can maybe explain that. Yes.
Yes.
Thanks.
Yes, please.
I'm
Yes,
Dimitris,
please.
Actually, how are you? So yes.
Hi, Dimitris.
How are you? It would be great if you can now all log out. I mean, you as a host chair end the meeting and then just return back to the same room, because we applied the patch and we want to see that the thing with the social rooms is fixed. Okay.
Okay. Okay. So everybody returns to the same room. Okay, great. I will end the meeting now and connect.
Feel free to use the social rooms and to socialize among you, and hopefully they will work as we plan to. Okay. Thank you very much.
Okay.
Thank you.